Well, a warm welcome to everyone and thank you for joining the webinar. My name's Dave Marshall-George. I'm the UK and Ireland Sales Director for Condair, and with me today is Paul Kipp. Paul's going to be answering some questions as we go through the presentation. We've many people on the webinar today from lots of different countries, so everybody will be on mute throughout the broadcast. If you do have any questions, please submit using the text question function in the control panel at the side of your screen. Paul will answer some of the questions as we go, and when the presentation is finished in around 45 minutes, I'll be addressing some of the most popular questions. I'd also like to draw your attention to the documents available for download in the control panel. There's the presentation in form of PDFs. So that'll be really useful if you're taking notes. There's the BESO green protocol, which when you're looking at recommended relative humidity levels in heritage applications is a really useful document. There's also a psychometric chart, which you can download and use digitally, which again is really useful, and our 10-point guide to humidification in heritage applications. So please feel free to download those as we go. And again, if you do have any questions, please pop them in the questions tab in the control panel. So, Condair Group, we were founded back in 1948 and we're based in Switzerland. We're a global leader in humidification and a leading manufacturer of dehumidification and evaporative cooling systems. And supported by science, we engineer individual holistic solutions that customers can trust through the entire life cycle. With optimal humidity, we increase productivity and create healthier built environments. Condair Group has production sites in Europe, North America and China, and its own sales and service organisation within 23 countries and represents worldwide. So with that, Paul and I are going to turn our web cameras off so you can concentrate on the presentation. And we will make a start on the presentation. So firstly, let's look at learning objectives for today. The first thing we're going to look at is, well, explaining humidity. What is relative humidity? Secondly, we're going to look at seasonal influences on humidity and also what affects indoor humidity, certainly in an environment such as a heritage application. Then we're going to look at humidity in heritage and why managing humidity in a heritage application is significantly important. We're also going to look at what's the ideal humidity for not just humans, but for different materials. And also how to manage humidity. What do we do to control the humidity in a space? Then we're going to look at the control technologies that are involved, whether that's central humidification, direct room humidification, or indeed dehumidification. So we're going to look at some of those, or all of those, should I say, all of those options. So let's start by looking at explaining humidity. What is relative humidity? What seasonal influences are on humidity, and what else affects indoor humidity? So on this slide, you can see we've got a blue dot, and that blue dot represents 5 grams of water vapor in air at 2 degrees C. So at 2 degrees C, 1 cubic meter of air with 5 grams of water in the air is completely saturated. It can't hold any more water. Now, if we increase the temperature to 10 degrees C, well, now the air is expanded, it can hold twice as much water, but the absolute moisture content has stayed the same. We haven't put any moisture into the air or taken any moisture out of the air, but the percentage saturation has fallen from 50%. And the actual level of moisture in the air we call absolute humidity. So there is a huge difference between absolute humidity and relative humidity. Absolute humidity is the amount of water vapor in the air by weight, and relative humidity is the percentage saturation of air. So let's say we take this one step further and we increase that air temperature to 20 degrees C. Again, we haven't taken any moisture out or put any moisture into the air, but we have the same absolute level of humidity. So with that 5 grams of water now in air at 20 degrees C, we're only 25% saturated. So it can hold 75% more water. So this can have a significant effect when we're changing the temperature of air. And that's what we're doing when we're taking air from an outside environment to an inside environment. So let's look at this a little bit closer. Here you can see a model, and in that model, on the left-hand side of the slide, we have air that's at 21 degrees C, 50% saturated, and 7.8 grams per kilogram of air. And we can see the column there represents that 50% saturation. And then we've got a wall separating indoor and outdoor conditions. And in this condition, we've got an outdoor condition of 21 degrees C and 50% and 7.8 grams per kilogram. So we know that if air travels from one condition to the other, we're still going to be within a specification. But let's say that outdoor air starts to decrease its temperature. And this could be either through a season change or indeed it could be between day and night. Well, when the outdoor temperature drops to 10.5 degrees C, the maximum moisture it can hold is 7.8 grams, and it would be at 100% saturate. So if we take that air and bring it into our air at 21 degrees C, we still have enough moisture content or absolute humidity in the air to satisfy the demand of the indoor space. However, let's say that now air is going to get even colder as we get into a winter season and the outdoor air condition drops. Here you can see the outdoor air has now contracted and reduced to 0 degrees C. And if we take that air at 0 degrees C, 100% saturated, 3.8 grams, and we put that inside, we're not going to be able to meet the humidity demand in our space. So if we take that 3.8 grams, we're only going to be at 24% RH. So in that case, we have to add moisture to the indoor space to increase the relative humidity up to the desired condition of 50% RH at 21 degrees C and 7.8 grams per kilogram. So we know, certainly in many applications, 21, if we're with set points at 21 degrees C and 50%, when there is the potential for outdoor air to be below 10.5 degrees C, we are going to have a humidification demand in the space, because as we put that outdoor air into the indoor space, we don't have the absolute moisture content in the air to be able to meet the set points in the space. This is the tool that some of you will be familiar with. This is the psychrometric chart, and we use the psychrometric chart to demonstrate the change or effect of a changing condition on air. Now, at the bottom of the chart, we have the dry bulb temperature as -10 up to 60 degrees C. And we have the wet bulb temperature going diagonally across the chart. There's 15 degrees wet bulb, 16 degrees C wet bulb, there's 20 degrees C wet bulb, and so on. And by these two temperatures, we can plot a condition, we can plot relative humidity and absolute moisture content and specific volume. So at 20 degrees C dry bulb and 14 degrees C wet bulb, we are at 50% saturated. So there's 50% saturated or 50% relative humidity. There's 60% relative humidity, 70, 80, and so on. So if we take our air at 21 degrees C, 50% RH, and we cool the air down, we're going to be following this line of process until we reach 10 degrees C. And we can see the effect of this process is that we're seeing a reduction in dry bulb temperature, But as we reduce the dry bulb temperature, the percentage saturation increases. So there's 50, 60, 70, 80, 90, and 100% saturate. So if air is at 10 degrees C outside, you can warm that back up and you will be in your condition. However, if the air is colder, then we're going to follow the saturation curve down the chart. As we follow that saturation curve, in this case, we're going down to 0 degrees C. Oh. Let's just let the slide catch up. As we go follow the saturation curve down to 0 degrees C, we can see the absolute moisture content has fallen, and it'll go down to 3.8 grams per kilogram. So if we've got an outdoor condition, 0 degrees C, 3.8 grams grams per kilogram, we know we're going to have to heat that air up to 21 degrees C. And as we heat that air up to 21 degrees C, we can see we get an increase in temperature, in this case of 21 degrees C, but we also get a reduction in relative humidity as we've gone from 100% saturated down to about 24% saturated. Now 24% saturated is going to be too dry because we were saying we've dramatically decreased the relative humidity. So we have to, in this case, isothermally humidify to get us to our set point. So we need to increase the moisture content by, in this case, 4 grams per kilogram and increase the relative humidity by 26%. And this is the cycle. If we've got a space condition at 21 degrees C and 50, and outdoor air is at 10 degrees C, then we'll be at saturate. As it gets colder, then the R rate will remain at 100%, but the percentage saturation will be, again, 100%, but our moisture content will be low. And as we heat that air up to 21 degrees C, our relative humidity won't be able to satisfy. So we have to humidify up to 50%. So what affects indoor humidity in a room? Well, there are many aspects. The first thing would be ventilation. So doors and windows and mechanical ventilation is going to be something of a consideration. We're going to have an air change rate. And UK building regulations states that for every person in the space, you're going to require 10 litres per person per second. So we know we're going to be bringing that outdoor air into the occupied space. And that amount of indoor air will be dictated typically by the maximum occupancy in the space. And we know that if the air is below 10 degrees C outside, we're going to have a humidification load on the inside to be able to maintain our condition. Weather, alongside the seasonal variations in temperature, rainy weather will have a huge impact on internal conditions, particularly when a venue might be empty 1 minute and then full, maybe with a busload of tourists with wet clothes and umbrellas fresh in from the rain. That's going to have an effect on the inside climatic conditions. And heating and cooling systems. As we've seen, temperature is linked to humidity. So any local source of heating or cooling will be affecting the humidity. Now, it's really critical that if we've got radiators in a space, that where we place artwork is not, that the artwork isn't affected by that dry sensible heat, because that dry sensible heat is there to heat the whole room. So you put a large amount of heat into a small space and let the heat dissipate. So you run the risk of having a microclimate around an artifact that will be dried out and then will expand and contract. So location of sensible heat and location of artifacts can be critical, not only for heating, but also for cooling as well. Solar gain, alongside factoring in mechanical heating, solar gain will also impact the indoor environment, very much depending on the U value of the glass, that is going to have a sensible heating effect inside the room. Again, that will depend on building orientation, the type of glass, and the surface area of the glass panels. People, as well as potentially contributing moisture via wet clothing, people naturally add moisture to a building through breathing. Now, typically, this can be calculated at 35 grams per hour for a person sitting, whilst this will rise to 110 grams per person per hour for somebody that has got a medium intensity of activity, and 185 for activities like exercising. So typically in a heritage application, we would expect to add 35 grams per person per hour. And then there is open water sources. Now this could be a fish tank or sink or any kind of water feature. So evaporation will take place and add moisture to the air. And the amount of water that will be added will be dependent on the temperature difference between the air and the water, and the surface area of the water, and the turbidity of the water in the tank or water feature. You could be evaporating a lot of water, or if it's a covered tank with close temperature to room temperature, then a minimal amount of water evaporation. And of course, then there's building construction and insulation, and this can have an effect. More typically, for high humidity applications, because certainly in the UK, if you've got poor building construction or poor insulation, then there's the potential for cold bridging across building materials. And when you get that, there's the potential to have a cold surface. So if you have a cold surface that's below dew point, and we know the dew point is 10.5 degrees C at 21 degrees C and 50%. So any surface that's below dew point of 10.5 degrees C, there is the potential for condensation to occur, and that is when we get into potential mold growth. So building construction can also have an effect. So next, we're going to look at humidity in heritage and why we manage humidity in heritage applications, and also what's the ideal humidity, and also how to manage humidity. Whenever we're looking at a heritage application, typically we are dealing with hygroscopic materials. Hygroscopic materials will lose or gain moisture. This will be the amount of gaining or loss typically depends on the equilibrium relative humidity of the material in question, which is another way of saying how much moisture is in it. What is the equilibrium relativity? Now we call it the equilibrium relative humidity because when the relative humidity in the air around the object is greater than the equilibrium relative humidity in the object, water will less readily leave. Whereas if the relative humidity outside the object is lower than the equilibrium relative humidity of the material, then moisture can be lost more easily from the material. So in a dry environment, moisture will more readily leave a material. So this can cause damage because we can get physical changes in dimensions. We get expansion and contraction as water is gained and lost. And that expansion and contraction can cause a tremendous amount of damage. We see cracking of woods, we see cracking of paintings, we see objects like musical instruments where you've got multiple woods and multiple glues all tied together under tension from strings. We get that expansion and contraction, and that can cause a tremendous amount of damage. And degradation over time as well. Even small swings can change the material, and expansion and contraction over time can have a cumulative effect on objects and artifacts, depending on the material involved. And benefactors may not permit loans and insurance companies to identify, say, travelling exhibitions. In fact, it's very common for an insurance company to request that the temperature and the relative humidity in the potential gallery space has been stable for 3 months before they accept that exhibition, so that they can guarantee that the climatic conditions within the gallery space are not going to affect the materials. And of course, we want to protect the fabric of the building. We don't want expansion and contraction in a heritage environment. We may have wooden paneling, we may have wooden floors, we may have wooden fireplaces that will expand and contract with changes in moisture content. So again, that can cause a tremendous amount of damage if we're not careful. So we have to consider the fabric of the building or the room that we're introducing dry, cold air into. So let's now look at, well, we know we've got a humidity demand, but what is the ideal humidity? Well, optimum humidity for human health is 40 to 60% RH. At this level, people feel comfortable and skin doesn't dry so readily, and contact lens wearers express less complaints of sore eyes, and static is largely eliminated. And importantly, airborne respiratory cross-infections are minimised, and this is due to our respiratory immune systems being most robust and effective in this range, and airborne viruses having lower infectious lifetimes in this range. So for people, 40 to 60 is ideal, and we can cope very readily with that swing of plus or minus 10. But people are super important to a heritage environment, but also it's really important to consider the materials in the space. So a typical band of humidity control for artifact conservation is also 40 to 60%. But with a vast array of materials in question and all the different levels of moisture equilibrium that these materials have, the ideal humidity for conservation is very much material dependent, as we can see from this visual guide. So you'll see a lower moisture content requirement for metal, so we want to avoid corrosion. Textiles, we would typically maintain between 30 and 50% RH to maintain the inherent structure of the fabric. And plastics between 30 and 50%, especially when plastics are attached to other hygroscopic materials, such as chairs with wooden legs, for instance. And photography. With photography, we've got paper, again, that will expand and contract with a change in moisture content. And that can either cause paper to, photographs to go curly on the edges as they take on too much moisture, or indeed curl up if they, to form like a C across the photograph, if we are in a low humidity environment. Stone, you can imagine, is much more robust material, but it will very much depend on the mineral composition of the stone as to what is the ideal humidity. And paper and paintings and canvases, a bit tighter, 40 to 55% RH. Glass, 40 to 60%, again, depending on the materials used in the glass production. Wood, a little bit tighter, again, very hygroscopic material, very often used with glues, and so under tension, so that will expand and contract, which we would want to minimize. And bone up at the higher levels. So these are recommended humidity levels for conveyation, and for a study that's done back in 1987, and it recognised that stone and ceramics with unstable salts were looking for 20 to 30% RH, and iron to prevent corrosion as a dry environment, so lower than 15%, and again, similarly, unstable or corroding metals, 10%. Minerals and rock fossils containing pyrite, 30 to 50. Lacquerwares, 50 to 60. Again, lacquer is applied to wood, so you have the potential of the lacquer and the wood expanding at different rates. So we'd want to minimize that. General textiles, 30 to 50%, as the reasons that we spoke on earlier. And ivories and bones, 50 to 60%. Parchment and vellum. Again, this is a natural material that will expand and contract to one of the largest extents, so 55 to 60 is recommended. Stretched paper, 45 to 55. Again, you've got this screen to think about. The wood that the screen is made of will expand and contract, as will the paper. And paper and photographs and films, as we spoke about earlier. So there is lots of advice. Now, this is really useful information, but of course you may have an application that has many of these materials in. So we may need to think about zonal control and individual control where we've got these individual materials, because if we've got paper in the same environment as iron, you can see there are very different conditions required. So over the years, different conservation organisations have researched, developed and published guidelines on how the environment inside museums and galleries should be maintained. And as I briefly mentioned, the general consensus currently is that 40 to 60% RH is the current optimal condition. But also variance is important. The indoor humidity should not drift up and down by more than 10% RH in any 24 hours. Now, the 40 to 60% is a recent relaxation of previously more stringent guidelines of 45 to 55%, with allowable fluctuations of plus or minus 5. But the relaxation of the range was in recognition of the need for a more energy efficient approach, and also an approach that was based more on the needs of individual materials rather than on a blanket range. And the most recent publication of the BESO Green Protocol, which is a leading voice on the matter, in 2023 highlighted this, with its view that the 40 to 60% range is really a starting point. And although the 40 to 60% range and 10% drift are still endorsed, the actual set points are at the discretion of the conservator's evaluation, and should reflect the needs of individual exhibits in a more nuanced way. This ultimately offers a more sustainable approach to the environmental control and conservation with a green first approach, but understandably, this is a more difficult goal for facility managers and HVAC professionals to deliver against. So once you've determined the desired humidity levels, how can this be maintained? Well, active monitoring of humidity at the point of need is critical. A complete room may have an undulating humidity profile. We may have stratification in the room, so we may have high humidities at lower points, and so that could affect artifacts that are lower or higher in the room. We may have solar gains to think about. We may have local sensible heat gains from heating or other sources. So active monitoring can be absolutely critical. We also want to limit water ingress using revolving doors or vestibules. Don't open windows. However, as already mentioned, building regulations specify a level of required ventilation. And in the UK, that's 10 litres per person per second. So keeping the outdoors out is never going to be a comprehensive solution to humidity management. Display cases or enclosures can also provide microclimates for exhibits that might have more extreme environmental needs, or for difficult to manage areas like entrance foyers. It's much cheaper to manage humidity in a small space rather than a complete room. Now, we may need various temperature set points to stay within humidity range. And as we've seen from temperature is intimately linked to humidity. So when there's the ability to lower temperature set points in the winter or raise them in the summer to remain inside the humidity range is a win-win situation. And this is a really interesting study at the Scottish National Portrait Gallery, where they recognised that we could maintain the equilibrium relative humidity in the objects by sticking within that 40 to 60%. And in the winter, you can run the gallery at a lower temperature, but still remain in that safe zone. And that means that you reduce your heating and humidification costs because we have a lower set point. And similarly, in the summer, they can maintain that relative humidity, but at a warmer temperature, so we can reduce cooling requirements. So this is summer-winter optimization. We feel slightly more comfortable at a lower temperature in the winter and more comfortable at a warmer temperature in the summer. So the environmental conditions within the space can be altered to reflect that change. And of course, humidifiers or dehumidifiers to increase humidity or reduce relative humidity. Now, if we've got in-room dehumidifiers and humidifiers, we need to make sure that there is a dead band between the set points of both, because each will have a control tolerance of maybe plus or minus 5%. So we need to allow that variance in the space and have a dead band between the two to make sure that they're not fighting each other. So what are the typical needs of a heritage humidity control application? Well, fast reaction time is critical. If we imagine a heritage application where we've got a coach load of visitors, perhaps they've been stood out in the rain or going from the coach park to the museum, they're wet, they come into the gallery and they start off and start a route around the gallery. Well, that will change the environmental conditions in the space by people breathing and evaporating water off their clothing. So we need the HVAC system or the humidifier to be able to react quickly to that change in the environment. And indeed, we have to look at each gallery space because we may need individual control in each gallery space as the environmental conditions in each gallery space change with people walking around them. Unobtrusive design is a really sensitive subject with a heritage application. Certainly in museums, curators spend a huge amount of time and consideration on the aesthetics and making sure that they can get the message and the details of their display across to the viewer in the best possible way. And sometimes putting a big humidifier in the way can not necessarily be the right thing to do. However, there are some considerations that we need to think about. If we're putting a humidifier in the space, well, we've got to be able we've got to have clearance around the unit so the humidifier can work correctly. There've been lots of applications where in-room steam generators have been used in museums, and the museum says, "Well, that's okay. We're controlling humidity very well, but I don't want to look at it." So there have been lots of applications where they've been screened and panelled in, and then problems occur as the units overheat because the humidifier should be ventilated. And also we need to ensure that there is clearance around the humidifier for steam to be absorbed into the air if we're using a steam system. So design can be critical, but not so easy, especially if you're in a listed building and there's no air delivery method. All of a sudden, hey, you don't have any choice apart from to have a mobile unit actually inside the space. The humidifier or the dehumidifier must have automatic regulation. We've got to be able to have a set point that can be set, and the unit will sit and control its output according to the needs of the space. And it should be tamper-proof. Now, it's critical in a public space that that we don't allow people to press buttons or interfere with the drain cycles or the maintenance regimes of the unit, or indeed the set points. So it's critical that it's tamper-proof and that it's safe. Now, a mobile unit in a public arena is absolutely fine, but a steam generator, well, that's a different kettle of fish. If we've got hot drain pipe work, if we've got the potential for people to put their fingers where steam's going to come out of, there's potential for scalding. So we really have to consider the safety and the hygienic side of the unit. So it has to encompass drain cycles, has to be maintained correctly, it has to have flush cycles so we're not getting any bacterial growth in the system. So these are usually part of the humidifier system itself, and typically best working when the unit is left in automatic operation. So it's controlling its own hygiene as opposed to just turning. Well, some applications you need a temporary solution as well. If you've got a temporary exhibition or you're moving artifacts from one space to another, it may be that you need a certain degree of mobility with a plant. So that's okay with mobile units, but if you're going to install in a plant room or in a duct or an air handling unit, then that really becomes an expensive decision to make if it is only for a temporary application. And of course, there's the energy that's required. Whenever we're humidifying, we're changing the state of a liquid, and we're either doing it using electricity or we're using it heat energy. So discussing what is the best low-cost, sustainable energy solution for the application, again, is critical. So let's now look at humidity control technology. We're going to look at central humidifiers, direct room humidifiers, and also dehumidifiers. So central humidifiers are used when we've got an air handling unit with an air delivery method, and inside the air handling unit we're going to have heating coils, cooling coils, filtration, and humidification. And here, typically, we're either using steam or water to increase the moisture content. And typically, it will be a humidifier like this that will be mounted next to the air handling unit or the duct, and the unit will produce atmospheric pressure steam, in this case by a cylinder that will hold water and conduct electricity through the cylinder, through the water in the cylinder to produce steam. Steam is then taken from the top of the unit through pipework to a steam lance that's inside the handling unit or duct, and we increase the moisture content by adding steam to the air at a prescribed rate. Now, you may think that as we're putting steam into the air that this will increase the temperature, but actually it only has a very minimal effect. You'll see an increase in temperature from an isothermal humidifier of about 0.5 to 0.75 of a degree. So very minimal, but we will see increased relative humidity as we increase the absolute moisture content in the air. Now, there's also different types. This is a resistive heater with inbuilt scale management, and that will typically be used where a closer control is required or where we've got questionable water quality, because you can use water treatment on these systems. So very common in let's say a museum application in London where we've got hard water, you do use reverse osmosis treated water and a resistance heater humidifier. And this will closely control the relative humidity, typically to plus or minus 5% RH. And then there are other options. There is a gas-fired unit if we're using gas, but with decarbonisation we see less and less of those now. Or in this picture here, indeed, you can see a live steam humidifier where a pressurized steam supply is available. It can be utilized. Here it's going through a valve to meter the steam into the air handling unit or the duct, and then there's a steam distribution system inside the duct that's releasing steam into the air to increase relative humidity. And the background picture that you can see here is inside a duct, and this is a short absorption distance manifold that's used to inject steam across the whole cross section of the air handling unit, because this controls the absorption distance. So the absorption distance is a critical factor when we put steam into the duct, because there is a distance required or a section length required that will allow the steam to be mixed with the air before any point where condensation could occur. So you get very fast, accurate control with these types of systems. It's very hygienic because we're using steam, but you do require an air handling unit or ductwork. And typically we're using electricity to produce steam. But there is another way. Instead of putting steam in, we can use an adiabatic system. Now, an adiabatic system evaporates water in the airstream. So it uses the heat energy of the air to evaporate in the air to evaporate the water. So what it means is that we need to preheat the air before the air hits the humidifier. So as air hits the humidifier, it evaporates water. So we see an increase in relative humidity, but a decrease in dry bulb temperature as we're sucking that heat energy out of the air to change the state of that liquid from a liquid into a gas. Well, typically these are higher capacity systems. You wouldn't consider a system typically for a duty below 30 kilos an hour because the equipment is just too big and your payback period is reduced. But if you've got an application where you can get that heat energy from, let's say, waste heat or ground source heat pumps, something like that, then these become a very efficient way of humidifying because, again, you just utilize that waste heat. So the running costs can become very small. Typically, this is what you'll see in a heritage application, in a main air handling unit. This is an evaporative humidifier, and it's got a tank of water at the bottom of the system. And when we get a demand signal, water is passed through this hydraulic module, through these lines, to an encapsulated spray bar at the top of the unit. Water then cascades over this porous material, and then as air travels over the porous material, it evaporates the water and cools the air as it goes. And that's fantastic. All you're running is about a small pump of about 0.25 kilowatts, so very efficient. But you do need to preheat the air. And that will typically give you plus or minus 10% RH control. But if you're better than that, then you would use a system that uses both a spray technology and evaporative technology. Here you can see a dual technology system where you've got a nozzle array spread across the whole cross section of the air handling unit. And when we get a demand signal, one or a number of these nozzles will spray water in a very fine aerosol. And that will evaporate in this section of duct or air handling units. And then any water droplets that haven't evaporated get caught on ceramic matrix, which then evaporate those water droplets off into the air. So it's a very efficient use of water, and it's a nice hygienic situation. But also by modulating the number of nozzles that are spraying at any one time, we get a very close control. So plus or minus 2% RH control. So it's very much horses for courses. What kind of HVAC system have you got? What level of controllability are you looking for? And where are you getting the energy from? Now, it might be that you've got a room with no HVAC system attached to it. You've just got, let's say, a conservation area or a storage room or an archive store, where perhaps you've just got some air conditioning but no air delivery method. Well, you can use an in-room system. And the one on the left here, that's just a small up to 8 kilos an hour steam production unit. And you've got a small orifice there for the steam to come out of, and then a control panel where you put in the set points and various other commissioning details. And for small archive rooms, these are really popular. Slightly bigger systems, you can use a standard resistive heater, as in the image on the right, with a fan box on the top to blow steam into the space. Again, you wouldn't put a system like this in a public area because we've got hot drain pipe work, we've got hot surfaces, we've got steam coming out of it, and we've got a control panel that can be interfered with. So we definitely wouldn't want to put those in a public area, but for archive stores, very common to see these types of units. And you'll get fast and accurate control, but just for a single area. You can use adiabatic systems as well. Here you can see a spray system that's utilizing a small spray head that can be attached to a local sensor and control valve, so we can have local individual control for many different zones running off a central water treatment and pump step. And you can have multiple zones, so if you've got different temperatures or different materials, you can run that humidifiers to work in sometimes 15, 16 different zones. And of course, they're low energy because you're utilizing the heat energy in the air, in the space, and very often we've got waste energy from lighting and heating and solar gains, etc. So we can use that to offset the energy running cost of the humidifier system. And very common is mobile units. So here, when we've got no air delivery method and we're in a public area, a mobile unit is an ideal situation, although we do have to get over the aesthetics. It's very difficult to hide these units, and so getting away from it, they are something that is going to be in a public area and on public vision. But they're ideal for a temporary solution, and they're adiabatic, so as low energy operation. Again, we're using the heat energy in the air to offset the adiabatic cooling, so they're nice and cheap to run, and it's a low cost installation. And you can have them plumbed in, or you can have them where they're just refilled manually. So a really good solution, especially if it's if you want to move them, so that they are mobile. Energy considerations for humidification. A pretty good rule of thumb is that for every 10 kilograms of steam that you're producing electrically, it's going to cost you 7.5 kilowatts of electrical energy. If we're doing that same 10 kilowatts with an adiabatic system and gas preheating, it's still the same 7.5 kilowatts, but the cost of the gas preheating is lower because typically gas is a third of the cost of electricity. If we're using a 10 kilo an hour adiabatic unit and we're preheating with waste heat, so if you exclude the preheating, hey, they're really cheap to run, 0.25 to 1.5 kilowatts. And it doesn't matter how big the unit is, you could be evaporating 1,000 litres of water and still have the same run cost for the humidifier itself. So these are all considerations that should be made when selecting. And of course, electricity nowadays, 47% of our electricity in the UK comes from a sustainable source. So that again can be a deciding factor. Could be decarbonising, so we don't want to use gas, or getting away from existing gas-fired humidifiers. So we've talked about humidification. Now let's talk a little bit about dehumidification. And when we do, there are two technologies that we talk about. There is either condensing dehumidification or desiccant dehumidification. And they're both totally different technologies. Now, in a heritage application, they are both types of systems are used, but usually in a different way. Condensing dehumidifiers are usually used in the space, and they're a box that you typically put on the wall and attach a power and a drain to. But inside that box that you're putting on the wall is effectively the same components as in your refrigerator or an air conditioning unit. So what happens is that humid air enters the unit, and the first thing that it comes across is a cold coil, an evaporator coil. It's called an evaporated coil because refrigerant is evaporating inside that coil. So it's lowering the surface temperature of that coil to a point below the dew point of air. And as soon as we go past the dew point of air, we know condensation is going to occur. So humid air is going to go over that cold coil. Water is going to condense onto that coil and then be taken away to a drain. So we now have dry air. Then we take the air over the condensing coil, which is going to put back the heat that we took out in the evaporator coil. So out the other side, we have warm, dry air. Now, it's a really important consideration to understand that you will always get a heat gain, because as condensation forms on this evaporator coil, the latent heat of vaporization will be released into the air. So as water changes from its gaseous state to its liquid state, so it condenses on that coil, heat energy is released. So with every type of condensing dehumidifier, you will always get a heat gain. And this should be considered in the design of the unit and the space. But minimal power consumption, here's a couple of pictures of them. This is typically what you'll be looking at. Nice aesthetic and clean box that will be attached to the wall, or it could be ceiling mounted, or it could be mounted in an adjacent room and ducted to the space. Inside the unit, you've got a filter here, and then inside you've got your evaporator coil, condensing coil. There's the compressor in there, and the refrigeration pipework and controls, and of course the fan for air movement. So they're pretty simple and quick to maintain. It's a filter change, and you may have to hoover out the coils annually, but apart from that, there's very little to do with them. But the big consideration is if you're looking for a lower humidity, the condensing unit will not do it for you. For applications where you're looking to control it around 20 degrees C and 50% RH, these are ideal. If you're looking for 15% RH, you'll never achieve it with a condensing dehumidifier because you're limited by the evaporating temperature of the refrigerant, making sure that it doesn't get too low where that can cause the condensate to freeze on the evaporator coil. So you're limited to typically, say, 19 to 21 degrees C and 50% RH. Two things, if you either want to go to a lower humidity or you've got a large HVAC system and you want to dehumidify all of the air that's going to a space, typically then you would use a desiccant dehumidifier. Now this is different again because with a desiccant dehumidifier, and here you can see a picture of one, and you can see there's two ports, there's a supply air and there's a regeneration air port. So what's happening here in principle is that process air is coming in typically from the air handling unit, and that process air hits a silicon wheel, a desiccant wheel, and that captures water molecules in their gaseous state. So that does two things. It dries the air out, but it also releases the sensible heat of vaporization into the airflow. So you get dry, warm air out the other side. So because you've got a heat gain there, you may have to consider post-cooling. So that air is then going to go either be mixed back with the supply air or go directly in line with the supply air. But then you've got a problem because you've got a desiccant wheel that's full of moisture. So how this is controlled is that we take an air supply from outside the room that goes through a fan over a heater, where we heat the air up to maybe 120 degrees C, and we dry a section of that rotor. We then take that wet air and then duct it out to ambient to release the water back into the ambient. So these systems are great for larger duties or lower relative humidities because we're not limited by a refrigeration cycle here. We can go down to dew points minus 30, minus 40 for specialist applications. But for a heritage application, it tends to be a larger application with larger air volumes and a central air handling unit. There's higher power consumption for these units, and this is really because we've got that electric heater for regeneration. They're simple to maintain. Again, a filter change annually, visual inspection. You may need to change the drive belt every couple of years. And of course, they're a ducted installation. So the system has got to have supply air ducted to it and return air ducted from it. And we can, as mentioned, operate down to very low dew points. And we can use electric, gas or steam for energy for regeneration. So if you've got those available to you, they may be worthwhile considerations. And depending on the set point, we may need pre or post cooling. But typically with these systems, you can get an accuracy of plus minus 2% RH if you've got a stable temperature plus or minus 0.5 to 1 degree C. So energy considerations for dehumidifiers. Well, 1 kilogram of condensing dehumidification will typically require 0.5 to 1.5 kilowatts. And 1 kilowatt of desiccant dehumidification, typically 1 to 3 kilowatts, again, depending on what power we're using for that regeneration. And we can utilize heat recovery on desiccant units where we take the regeneration air and we pass that through a heat exchanger to preheat the regeneration air. So system design and selection and consideration for energy is a critical factor. So when we look at the stages in a project, firstly, when we get involved in a project, then we'll go through the consultation stage, where we'll look at the fabric of the building, we'll look at the internal, the HVAC system, or whether there isn't an HVAC system, and we'll look at the energy sources that are available to you, and the quality of the water that's available, and the type of control tolerance that's required in maybe different sections of the application. Once we do that, we'll go through a product sizing and selection process where we'll be establishing what's the air change rate or the fresh air rate going into a space, and we'll be looking at the difference in absolute moisture content between winter and winter design and internal set point. So we'll know how much air we're dealing with and how much moisture that we're going to have to add to the air. And we'll then look at the other considerations for controllability for selecting the correct equipment for the application. Then, if we're doing the installation, there'll be a fully managed installation with full health and safety RAMs and risk assessments, and will be managed by an installation manager and a team of professional installers. Then, of course, you hand over to the commissioning team to make sure the integration and installation is correct, and training and handover with the client. And then to ensure that the client's getting the right value and service out of the machinery for the lifetime of the machine, then we will be a service and maintenance schedule to implement. So we at Condair, we do humidification. You can see a picture of a large humidification system in a paper mill to make sure the equilibrium relative humidity of the paper is controlled. And we get involved in dehumidification, be that desiccant dehumidification or condensing dehumidification, or indeed evaporative cooling, where we're either evaporating water into a large space or more typically into something like a data center, where we're utilizing that evaporative cooling effect of evaporative coolers. So in summary, we looked at humidity control in heritage sites. It's a necessity. We know that as we're putting moisture into the air from outside, unless the moisture content outside is the equivalent to the required absolute internally, we know we've got an adjustment to make. And we required humidity levels can vary between 40 and 60% typically. And use of technology alongside other activities to manage humidity is critical, and many options are available depending on the application, the energy source available to you, and the existing infrastructure of the building as far as the HVAC system is concerned. And of course, expert advice and support is always available from ourselves. So with that, we've got a little bit of time now to hopefully we've got some questions. So I'd like to welcome Paul back. And thank you, Paul. You were kept busy in the background there. And,
certainly was. Some interesting questions. A lot of interesting questions come through. Yes.
Fantastic. Well, let's attack those. See if we can come up with some answers.
Okay, right. So one of them you might be able to answer. Two of them you may be able to answer with one aspect actually. Regarding water quality, are there any specific requirements on water quality that affect the different types of humidifier? And also, how does water quality affect the maintenance of humidifiers?
Both really important questions. Water quality can have a dramatic effect on the humidifier, and also depending on the type of humidifier. So if we're using electric steam generation, let's say with an electrode boiler, we're looking for water quality between 125 and let's say 600 microsiemens. It is important that in a hard water area, softened water is not an ideal option. If we soften water, we're just replacing the calcium with sodium, and that can have effects on the capabilities and the boiling cycles and drain cycles of the humidifier. So you'll not only see loss of humidity control from introducing a dilution cycle, but you can also then corrode internal components with the humidifier. With regard to other types of humidifiers, if we're using an evaporative media humidifier on an adiabatic system, then mains water can be used, and mineral buildup in the unit is controlled by flushing cycles within the unit. But if we're spraying water into the air, then we must use reverse osmosis water treatment. If we don't take the minerals out of the water, then the nozzles will block up and the minerals will fall out of the water as it evaporates, and you will then get mineral buildup inside the air handling unit, which can be a source of bacteria, of food for bacteria. So again, with a spray system, we must use water treatment. With an evaporative system, that can be done internally in the unit, so we can use mains water. And then with a steam system, mains water can be used unless really close control is required, and then a resistance heater with reverse osmosis treated water to minimise drain cycles. Did I cover everything there, Paul?
Yes, that's great. Yeah, we also had a number of questions from different people actually. Excuse me, about the optimum level for preservation of artifacts. Really, I guess there is a certain level. I mean, obviously, Dave, you can tell us what that is, but also different artifacts will require different levels of RH. I believe we have some details on that that we can forward on to people. So a lot of people actually ask that.
Yeah, well, again, the different materials, there are just such a plethora of different materials that are involved. We did give some details in the presentation. So anybody who wants a little more of those details, please download a copy of the presentation, and it lists those details of those different materials out in those slides. And there's everything from paper to stone and glass and wood. So it will very much depend on the material in question. And again, it's about maintaining the equilibrium relative humidity in the object.
Sure, yeah. Okay. Maybe you've got time, maybe, for one more?
Yeah, let's squeeze another one in.
Okay. Somebody has asked about what is, can you elaborate on the evaporation distance within an air handling unit of a humidification system?
Yes, I can. Yeah, this is the distance, in fact, typically with steam, and it's the distance where steam leaves the steam pipe to where it's fully mixed with the air. So you will see a visible plume of steam coming off that steam pipe. Now, the length of that plume, or the absorption distance, is critical, because if we put any object in the way of that before all the steam has evaporated, we can get condensation forming. So you'll get water in the air handling unit. Now, to calculate what that absorption distance is a factor of the length of the steam pipe, the amount of holes in the steam pipe, the dimensions of the air handling unit, the air volume, and the velocity of the air temperature, and the moisture content before and the moisture content after the steam pipe. So there's about 9 factors that we have to consider when we calculate that absorption distance, up to and including the fact that we need to know what's happening after that absorption distance, because if any filtration is involved after that absorption distance, then typically we can need up to 2.5 times that absorption distance allowed for in our section length. So this is really about the straight section of duct or air handling unit section that's required to make sure that we're free of obstruction, to ensure that we don't get any condensation in the duct.
Yeah, great. Thank you, Dave.
Perfect. Well, we've run over a little bit, so apologies. And once again, can I thank everybody for joining the webinar? And again, don't forget those downloads, and everybody that's attended the webinar will get a link in about an hour's time to download an attendance certificate for your professional, continuing professional development.
Any questions that you've asked that we have no chance to answer, we can obviously forward those on to you.
So thank you, everybody. Thank you, Paul. And
Thank you.
I look forward to seeing you all at the next webinar.